Hello again and welcome. I've integrated the new eye diagram feature into my Solver software, so I thought today we could go over how that works, and then we can run a few experiments with the LiteVNA as well. So one of the things I'd like to mention is this LiteVNA still has the latest firmware. Again, this is version 1.3.07. The file name is LiteVNA 64-2202228.bin. So I've been testing with that version for a couple of weeks now. I haven't seen any problems with it, so my plan is to just stay with that version of firmware. As I had mentioned earlier, I was running a pre-release version of Dislord's firmware because it corrected a problem that I was having with the automatic gain control, and again, that's been included with the firmware that I'm testing now. So in the first video I had mentioned this book by Bonagide and Jarvis, and then I went over this section that talks about how this calculation is performed. Again, starting out taking the S parameter data and then doing a inverse FFT, and then the eye diagram is calculated by convolving the time domain response with a predefined pseudo-random bit sequence. So I also have Dunsmore's book. It has a section on eye diagrams, and of course, just to be clear, this other book has a lot more data on eye diagrams as well. But you can see he talks about what an eye diagram is. But as I kind of went through this doesn't provide the basic math that's required to actually do the calculation. I was quite surprised by that. So one of the things that I did get out of Dunsmore's book, this is on page 266. Recently there have been software packages that can take S parameter data and provide the equivalent of an oscilloscope measurement of the output signal, as though the ideal input signal has been applied, and present the result in an eye diagram. In fact, these software packages can process either time domain data from an oscilloscope or S parameter data from a VNA. In many cases, the signals are fully differential, such as low voltage differential signaling. Keysight's physical layer test solution is one example of such a program that can utilize previously measured data to generate these equivalent eye patterns. So I went looking for this piece of software, and Keysight still offers it on their website. Unfortunately, when I went to try to get a license for it, it seems that their website's broken. So I wasn't able to actually try this thing out. It looked like they offered like a trial license or something at one time. Unfortunately, I couldn't get it working. The other thing I was going to do during this video is, again, I have an old PNA. That PNA can be upgraded by software to increase the range to 9 gigahertz. Unfortunately, it requires a license key, and talking with Keysight, they no longer offer it. So while I had originally planned on using that as part of the benchmarking during this video, unfortunately, I can't show it to you. So I'm going to try to keep this video under an hour. So why don't you go grab something to drink and we'll get started. Alright, we'll go ahead and we'll load up our Solver32 software. Again, this is the 32-bit version of it. Notice we have a 64-bit as well. Again, that is not supported. We'll select our defaults. And now what we can do is go ahead and change our stop frequency to 9.3 gigahertz. Again, this is the upper frequency of the LiteVNA. And we don't need 801 data points. What we'll do is just dial this back to 201. We'll go ahead and select sweep. Now we'll go ahead and select advanced, and this is looking at the step and impulse diagrams. Now what we can do is attach our 70mm homemade Beatty standard. Again, this is just a section of air line. Transmission line is made of brass tubing, and it's got a step function in it that's essentially 70 millimeters long. Now let's go ahead and turn off our auto scale for the vertical axis, and we'll manually zoom into this a little bit. Again, keeping in mind that the instrument has not been calibrated, but you can see we can basically see the shape of the waveform starting off at 50 ohms, working its way down to 25 ohms roughly, and then it's an open circuit on the back side. Let's go ahead and select impulse. We can enable our markers, and let's drag those to the peak into the valley. And you can see our full width half height right now is 138 or so millimeters. So that's not correct. Let's just drag the right cursor to the peak to the left of it. And you can see now it's displaying roughly 71 millimeters. Fairly close. Again, this is a homemade standard. It starts off at 50 ohms, again to 25 to 50. Now let's go ahead and terminate the backside of our Beatty standard. Again, that's a 50 ohm terminator. Let's go ahead and turn off the auto scale for the vertical axis. You can see how it's kind of ramping up as we go up in higher frequencies. Again, this is a result of it not being calibrated. So let's go back to the main page. And now let's load up a calibration. So we'll select again 2-port cal, old. We'll go to our calibration directory. And we'll use the 50 kilohertz to 9.3 gigahertz SolCal. Still looks like random gibberish. You can see it's calibrated now, and that calibration file will automatically set the VNA for the start-stop frequency as well as the number of data points. Now you can see as we go to advanced time domain, looking at the step, it's actually quite flat. And you can also see it's hovering right around 50 ohms. And our step is around 24 ohms or so. Let's go ahead and turn off our calibration again. And now let's remove our Beatty standard. And we're just going to replace it with a through. And now let's go back to advanced. Now let's go ahead and select TDT. Again, TDT would be transmission, where R would be reflection. Let's go ahead and create a waveform. Again, we'll change the number of random data bits to 500. Again, this is a perfect waveform, essentially. There is no rise time or fall time. Let's zoom into this a little bit. So the red waveform, again, represents our phase lock loop. And you can see it's locked to this signal quite well. And this is looking at our eye diagram. You can see I show various metrics for this data as well. Again, this is all live. Let's change the data rate to 500 megasamples a second. Now let's change our overlap to 10%. You can see how it changes our eye diagram. Again, this is just selecting how much of the adjacent windows that we're going to display. We'll go ahead and change it back to 50%. Now let's change our data rate to 1 gigasample per second. And this is looking at 2 gigasamples. Here we are at 5 gigasamples. You can see how the eye is starting to close up. Let's bump it to 10. The eye is starting to get really closed now. Here we are at 20, and you can see we've lost lock. Let's just go back to the random generator, and you can see it's just basically noise now. Let's go ahead and we'll take it back down to 15 gigasamples. You can see we still can't obtain a lock. Here we are at 10 again, and you can see it's locked, but the eye is quite small. Let's go ahead and change our number of random bits down to 300. And let's select PAM4. Again, this PAM4 is going to have 4 discrete levels. You can see again that we can't obtain a lock. Again, if we reselect NRZ, everything's back to normal. Let's go back to the main page and let's go ahead and calibrate the unit. Let's start with our 50 kilohertz to 6.4 gigahertz. And again, you can see how it's changed the start and stop frequency to reflect that. And we're still at 201 data points. Again, we'll go to advanced. Now let's regenerate our pseudo-random sequence. And this is what it looks like. So at 10 gig, let's try it at 20. And you see we still can't obtain a lock at 20. But again, we're not running the VNA at its highest frequency yet. Let's just go back to the main page. Let's load up our fastest cal. So again, 2-port cal, old, and 9.3 gigahertz. And again, you can see how that's changed our stop frequency. And again, we go to advanced. And let's go ahead and let's change the number of data bits down to 100. And you can see how the eye is now opened up a little bit. So we're actually seeing a lock now at 20 gigasamples. Let's go ahead and increase this now to 300 random bits. You can see it's doing an okay job trying to lock. Again, there's a lot of noise, so the eye is closed quite a bit, but again, this is 20 gigasamples. Now let's select our PAM4. And it doesn't look very good still, but you can see that it is trying to lock to this. There is somewhat of an open eye for the 4 different levels. If we change it down to 1 gigasample, you can see how the eye opens right up. Let's go ahead and change it back to 10 gigasamples. And you can see how the eyes are closing back up again. 1 gigasample, it's very clean though. Again, let's just return to NRZ. Almost looks like a perfect square wave here at 1 gigasample. Notice the rise in the fall time. Down around 30 picoseconds is what it's claiming. Again, this is going to be a limitation of the upper frequency of the nano. Let's go ahead and remove the through again. Notice how the system loses lock. Notice how it automatically turned off the sweep. Basically, the software is looking for the amount of time that it takes to execute that routine. There's a timeout in there, I think right now, of 1 second. If it takes longer than that, it aborts the operation and turns off the sweep. Basically, what I'm trying to do is not overload the PC. Now let's replace our through with our Beatty standard again. We'll just place it between port 1 and port 2. Now you can see the effect of that 25 ohm section in the Beatty standard. We can go ahead and change the data rate to 2 gigasamples. And here again it is at 5 gigasamples. And here it is at 10 gigasamples. Notice again how the eye is starting to close up. Notice too how you kind of have a bimodal system. Again, it's either at 50 ohms or it's at 25. Next, we'll replace our Beatty standard with our homemade through standard. Again, this is just a piece of FR4 material. You can see our eye is opened up fairly well. Again, this is at 10 gigasamples a second. Now what I'm going to do is just move my finger close by the transmission line. You can see how the eye starts closing up, and eventually we lose sync. Again, this is obviously all live. I also support a mask feature. This is automatically generated. The software is looking at the eye's width as well as the height, and it's placing this mask within inside of 20% of that. It also sets a upper boundary as well as a lower. Now you can see as I'm moving my finger, we're starting to see a failure. You can see how the failures get set to a 1. Normally the failures would actually count the number of faults, but notice that it never exceeds 1. We can also save these masks. We'll just select the mask tab. We can select save. Now we can clear the mask. Let's change our data rate. We'll go down to 1 gigasample and we'll generate a new mask. Now let's change our data rate back to 10 gigasamples. You can see our mask off to the right. You can clear it out again. We'll just go back to the mask tab, hit load, load up our original mask, and go back to the eye diagram, and here's our original mask again. Again, there's no limit to the number of masks that we store. Again, I had mentioned that we have this fast mask. Let's go ahead and disable that. And now what I'm going to do is move my finger over the transmission line. See how the number of failures is actually counting up now? It's a lot higher than 1. That's because this routine is actually looking at the geometry of the mask and comparing that against the waveforms. Let's go ahead and we'll change the data rate down to 5 gigasamples a second. And you can see how the mask stays the same size. We'll generate a new mask. Now let's change the amount of overlap to 10%. And notice how the mask proportionally changes its size. Here it is at 90% overlap. And let's just return back to 50%. So while I do show more data as far as the number of failures when you disable the fast mask, it requires quite a bit more processing time. Let me just bring up Task Manager and I'll show you what this looks like. You can see right now we're burning about 60% of the CPU. Now let's go ahead and enable the fast mode. And you can see how our CPU usage has dropped all the way down to 9%. Let me go ahead and move my finger back over the transmission line to cause a fault. And you can see that really doesn't affect the CPU usage. Now let's disable the fast mode. Again, we're back up to about 56% or so. Now, as I slow down this data rate, you can see that pushes our CPU usage all the way up to 90%. Alright, let's go ahead and we'll clear the mask. Now you can see how the CPU usage drops all the way back down to 9% or so. So again, this mask routine is pretty CPU intensive. So what I'm doing with this fast mode is instead of looking at the geometry of the mask, what I'm actually doing is looking at the individual pixels when I'm drawing the mask, and I'm looking to see if there's any other data on the screen where that pixel is anything other than black. If it is, I consider it a fault. So doing that kind of a binary check versus looking at the geometries of the mask and the waveforms, it's a lot faster, and obviously it requires less CPU usage. I'd like to test a different circuit, and we're going to be using my LeCroy 7200. This particular scope has a 4 gigahertz plug-in installed. Nice thing about this particular plug-in is it's capable of doing TDR measurements. We'll go ahead and turn on the scope. This is the circuit that we're going to be analyzing. This is just a mini circuits ZFR SC-42S. This splitter is rated for DC to 4.2 gigahertz. We're going to use the S port here as our input, and then it's going to split off to a 22 picofarad capacitor, and on the other side we'll go to the second channel of the oscilloscope. Okay, we're going to start with just a jumper between channel 1 and 2. What I'll do is go ahead and turn off the A plugins channel 1 and channel 2 as well. And then for B1 channel 1, we'll select display and then vertical setup. And then down here we can select pulse. And you can see it's now putting out a square wave. The edge rates on this waveform are quite fast. We can go ahead and we'll zoom in a little bit. Alright, you can see we have a rise time of about 160 60 or so picoseconds. Now what we're going to do is install our circuit. Again, with this capacitor, the idea is that we're going to slow that edge rate down quite a bit. And here's with our circuit installed. I'll just go ahead and zoom in a little bit. Just looking at our rise time, you can see it's calculating roughly 2.8 nanoseconds. And looks like our fall time is also roughly 2.8 nanoseconds. Notice this little disturbance on the fall is also present on the rise. Again, with my software for the VNA, we're trying to synthesize a perfect signal. Of course, the TDR pulser on this has a certain amount of rise time and fall time, but it's quite a bit less than what the circuit is that we're testing. So what I'm expecting is we hook this circuit back up to the VNA. We should be able to measure that same rise and fall time. So let's just see if that works out. Alright, we'll go ahead and restart our solver software. Again, we'll load the defaults. And let's go ahead and link to our LiteVNA. And we'll go ahead and calibrate it. Again, we'll select old, calibration, and we'll use the 9.3 gigahertz range. We'll re-enable our sweeps, and again we'll select advanced, and we'll select TDT. We'll select our random generator. We'll set the number of data bits to 500, and we'll go ahead and create that. And now let's zoom into this a little bit. Notice how that waveform is basically identical to what we saw on the oscilloscope. And now let's select the eye diagram. Look at the rise time and the fall time. They basically match with what our LeCroy oscilloscope shows. Very close anyway. We'll change our overlap to 10%. So very similar to what we're seeing with an oscilloscope. Again, that oscilloscope is a 4 gigahertz bandwidth. So this is a second circuit I put together to test our eye diagram software. This is the schematic for it. So essentially it's nothing more than a splitter, and then you can see I have a small tank circuit. This tank circuit is made up of a 10 nanohenry and a 39 picofarad capacitor. The inductor is made by Coilcraft. It's part number 0805 CS100XJL. The capacitor is made by American Technical Ceramics. This is a part number ATS 100B 390J. So I had simulated this using microcap, where the other one was critically dampened. This one we're going to actually generate some overshoot, hopefully. So the amount of overshoot is basically going to be 30% higher, and the same thing for the undershoot. And as this rings out, the very first dip should be roughly 2.9 nanoseconds out. The second dip is at 7 nanoseconds out. And the third dip is roughly 11 nanoseconds out. So right here is our inductor. Here's our capacitor. And then these 5 resistors here make up our splitter. Let's go ahead and we'll zoom into this vertically a little bit. Bring our offset down. And it looks like our peak is indeed roughly 30% higher. Notice our first valley here is basically 1.5 divisions over, and we're currently at 2 nanoseconds per division, or 3 nanoseconds out. Here's our second dip, which is 1, 2, 3, 4 divisions out. So just shy of 4 divisions, or yeah, probably roughly 7 nanoseconds. And right here you can just see our third valley, and again that's 8 divisions out, or just shy of 12 nanoseconds. So it seems the circuit actually matches our SPICE simulation, except for notice this little spike here at the beginning. Our simulation doesn't show that, but of course the circuit board and all these components are going to have parasitics that are not modeled in my SPICE simulation. So what we'll do next is connect the circuit up to our VNA and let's see how it performs. So this is the circuit that we just ran on our oscilloscope. Again, we have a tank circuit of a 10 nanohenry in parallel with a 39 puff, and that's just attached to one leg of the splitter. We have a 50 ohm source impedance. This is looking at our pulse that's driving it. It's essentially just a square wave. There is no rise or fall time. This is our transient setup. Let's go ahead and zoom into the waveform a little bit. And we can set some markers. So let's just look across the horizontal axis. And let's look at the first valley. You can see it's again roughly 3 nanoseconds out. This is what we measure with the oscilloscope. And again 7 nanoseconds, which is what we measure with our scope. And here's the third valley at about 11 nanoseconds, again matching with what the oscilloscope shows. You can also look at the peak height to see how much kind of overshoot that we have there. Again, this is roughly 30%. We can measure it again with the marker. See, it's roughly 190. And let's look where it goes steady state. And it's about 124. So yeah, somewhere around 30%-ish or so overshoot. So the simulation basically matches with what we're seeing on the oscilloscope. And again, we'll use the 9.3 gigahertz. You can see we're 201 data points again. And let's select transmission mode again. And we'll change our data rate to 50 megahertz. Now again, we're trying to look at a waveform that's settling out at basically 11, 12 nanoseconds. So we have to really push this thing down in frequency to look at that. So at 50 megahertz, we're at 20 nanoseconds. So you can see we can't see quite all of the data. Let's zoom into it a little further. And you can see we're at 77 where we start. And that first dip is at 80, so 3 nanoseconds over for the first dip. Second one is at like 85-ish or so nanoseconds out. And then the next dip would be probably about 89 nanoseconds or so out. So very close to what we're seeing with the oscilloscope. This is looking at our falling edge. Again, the two should be basically the same. Notice how we see that initial peak like we saw with the oscilloscope. And again, we don't model all the parasitics. But notice the number of data points. It's at 197,000. If we change our frequency lower, notice how this range flag gets set. Basically what I'm doing is I'm throttling the amount of data that the software processes. Again, what we're trying to do is prevent the CPU from becoming overloaded. So that's the reason that I'm showing this particular circuit is there's actually a lower limit as well as an upper limit that we can measure with the LiteVNA. Again, the LiteVNA is rated for 6.4 gigahertz. That would give us a rise time of 156 picoseconds. Using harmonics, they cap it off at 9.3 gigahertz. That gives us a rise time of 107 picoseconds. With the one that I own, I seem to get reasonable data up to about 8.4, 8.5 gigahertz, so somewhere around 120 picosecond rise time. So what I have here is an old military low-pass filter. It should give us a rise time and a fall time of about 1 nanosecond. So let's just see what we get using our old LeCroy scope. It looks like our rise time is between, call it 1.1 and 1.2 nanoseconds. Again, if we look at the fall should be basically the same thing. Yeah, so 1.1, 1.0. So again, the pulsar on this scope isn't perfect. So here I just have our piece of coax strapped across the 2 ports of the scope. And again, we can see our fall edge rate is roughly 101, maybe 110 picoseconds. And again, if we look at the rising edge, it's about 170 or so picoseconds. But the LiteVNA should measure roughly a 1 nanosecond edge rate with this filter attached. Alright, again, we'll just reattach our filter to the LiteVNA. And again, it's just going between port 1 and port 2. Again, we're just going to load the light with the 50 kHz to 9.3 GHz file. And we'll begin the sweep. And let's go to advanced. Again, we'll select the transmission mode. We'll change our data rate to 250 megabits per second. And let's go ahead and select the data generator. And we'll set this to 300 data points, I guess. And create. And now let's go ahead and display the eye diagram. And there you have it. So roughly 1.05, call it nanosecond rise, maybe 1.06 nanosecond fall. Again, the scope, that pulsar I think is an Echo drive and it's not symmetrical. The output of this is symmetrical. So even though it's kind of a quasi square wave at this frequency, because it is symmetrical, we do get the same rise and fall time. And again, the signal that I'm synthesizing, of course, that's going to be a perfect square wave. We can change this frequency. Let's bump this up to 500 megahertz. Let's try it at 2 gig of samples. And again, you can see that we're going to lose lock with this. If you're curious, just an FYI, this filter has a cutoff of 500 megahertz. Well, I think that's going to be it for this video. Hopefully this gives you some idea of what you can do with this new feature and how it works. I don't have the software released yet. I'll probably spend a little bit more time testing this before I go ahead and cut it loose. But you can expect it up there in the next couple of weeks. So that's going to be it for now. So we'll see you in the next video. Till then, later.